Um, Last time I think we wrote the general solution of the Maxwell equations, right? In terms of the vector and scalar potentials. And so it's integral over the volume. So this big R is the distance between the observation points and the point within the volume where the charges and the currents are located. So it looks just like the usual solution for the static problem, but you have to remember that everything is done at the retarded time, meaning that t prime is not equal to t prime here is not equal to the time t, but is the retarded one. So it's t minus the time it takes for the signal to reach the observer, because everything propagates with a finite velocity. In fact, the velocity of light. We have a completely similar result for the scalar potential. The only difference is that you integrate over the charge density. Again, in the volume R, so if this is the volume R, here's the distance R, here's the observation point T, and again at the retarded time, right? So in a way we are done, because we wrote the Maxwell equations. Now we have solved them, so everything is just a matter of writing this. But you see that if this distribution is complicated, you may have some problem in doing the integrals. And anyway, let's study some examples, right? And so I think this is where I stop on Friday, right? Or and so the next thing I want to do is, okay, so this is the general solution. Now let's see some, I don't know how to call it, application. An application. So let's start with the simplest. You see, this is just an arbitrary current and arbitrary charge density. So you understand that the simplest case would be what? Well, I guess one of the simplest cases would be if we take a single charge, right? Let's take the case of a single charge, Q. And because we want the simplest case, I mean, you understand, this could be a single charge, but moving arbitrarily, accelerating, doing whatever the charge wants to do. But let's just stick to the simplest case, that the charge just moves with constant speed. As we will see, in order to have radiation, you need the charge of the charge distribution to accelerate. So this is sort of the simplest, because then you don't have radiation from this system. And we want to find the fields in this simple case. So we have a single, so here is our observation point, this R at time t, and we have to be careful, because you see R, so the position of this point here, let's say is R, and this is R prime, and here's the same charge. So this is the point P at the time t, the charge is here, but at the time t prime, the charge is back here. Okay? So this R divided by C. So this is the present position. Actually, R prime here. So you see, all the time you have to worry that you are computing the field here is not the field produced by the charge at the time t, because the charge at the time t is here. But the field here is the one that was produced by the charge at the time t prime, that is a little bit before. Because this moves, and then the field propagates, and when this is here, then you are hit by the field here. So all the time you have to worry about this retardation. That's what makes the problem not equal to the electrostatic or magnetostatic problem, okay, where you have just a single time. Okay, so let's see how these integrals are done in this simple case. Now you see that because we have just a charge, right? Yes. It's just it's the time from here to here, so I call it R prime. Because I call R this, so this is R prime. But because before, this is just two arbitrary. If you start here, this will be R, and that will be R prime. Then this will be R minus R prime. I mean, if you prefer, you can call it. But then you have to measure from some. It's because I started from here measuring position, then that is just R prime. Yes? I mean, if I start here, I call this R, and this is R prime, then this distance is R minus R prime. So you see, then I just call it big R if you want. So for a single charge, right, I know how to write the current, and particularly the charge density, but you see the problem is that, so if you didn't have this retardation problem, then the infinitesimal charge produced by an infinitesimal volume of would be just okay, it would be just rho t r prime d3 r prime, right? But this is not true, right? Because the dq producing the field is not just the dq. I have to worry about the retardation, because you see, as let's take the sorry, assume that this charge density is in a small volume that is a cube, just to make it simple, right? And this charge is moving, okay? So you see, as you take this integral, so to speak, the charge has moved a little bit. So it's not any longer there. So you have to keep track of this as you do the integral because of this retardation. So you see, actually, the effective charge contributed, infinitesimal charge contributing at the point P at the time T prime, that is the retarded time, is not just this. You have to subtract the amount of charge that either has moved away or it has moved in while you were doing the integral. So let's assume that it's moving this way, so it's moving out from the original. So I subtract, this is the charge density minus this factor that I'm going to write here, and I'm going to explain it in a second. Okay. Why do I have this correction factor? You see, because as I said, assume that you have your charge and it moves something like this, a distance, let's call it b. So let's assume a one-dimensional problem. And it was a cube, so it started out with these four sides equal to a. So in the time at t prime, it moves by a distance b. And how much is this change in the volume? Well, you see that b is equal to a plus v, the velocity of this, the delta t, that is the time through which you are integrating. And how big is this delta t? The delta t is exactly this r minus r prime divided by the velocity of light. So you see when you rewrite this, you get this extra factor. So it's like in relativity, this comes about because of it's like a Lorentz contraction, but I mean you can understand it from this argument. So it's not true that you just plug in the value of this charge here. You also have to take into account that, so to speak, the volume is contracting because of this retardation. So you have two effects. And therefore, so let me write this. I can collect now the two, right? And it's, as I said, it's 1 minus this factor, r minus r dot. Sorry, here I forgot the v that I had. Divide by the length c. And this is d3r prime. Okay? So now I can write the solution for the scalar potential, because you see now the scalar potential is just the integral of this small charge over the volume. So I get the potential in R is going to be minus or depend, well, 4 pi epsilon. What? This is dq, right? So I have to do the dq, but the dq is given there. Divide by this distance. The distance is what it is. This big R that is minus. Right. So if I plug in this, I get the, you see, the dq, it becomes just the total charge, right? Because it's this integral here. So I have the charge plus minus, depending on the sign of the charge. Then I have this overall factor. So this would be just what? It would be just the potential of the Coulomb force, right? But you have this extra factor that I write in this form. You see, if I call, so let me call, you see, this is, let me call V this quantity here, that is the component of the velocity along the distance here. So then I can just write 1 minus V divided by C. And of course, it's at the retarded time. So there are two effects. It's true, it's like the Coulomb potential, but computed at the retarded time. And because of this, I also have this extra correction factor, sort of. Similarly, I can write I can do the same for the vector potential, obviously. And I get essentially the same, but with the velocity here, because this is the current produced by a point charge. So it's the same thing, but so these are, they have a name, Lienard and Weckert potentials. This was a Frenchman and a German, linear vector potentials. So they are the potential of a point charge moving with constant speed. So that's a nice, and so those are, they are kind of interesting. I mean, and just to make them, guess I still need this. Leave it here. Well, anyway, it's a homework to rederive them. So, well, they are in the book. No, don't worry. And so, in fact, this is the exercise that you should try and do by Monday. So okay, derive the well, we already did, so, right? But given the, so the exercise, I guess, is given the linear Vickers potentials, compute the, derive the, the field intensity, that is E and B. And discuss the result. Discuss means that you should notice how they are, the way they are. Okay. From the potentials. So rederive the linear vector potential. Then when you know the potential, you know how to get the E and B fields. Then look, well, essentially I want the angular distribution of these fields. How do they look? You will see, it's interesting. So the next step is, so here essentially you have a point particle moving with this velocity, and you can compute the potential. So the next interesting example on which we can discuss these general solutions is if you have a localized source, J and rho, oscillating, right? Because that is an accelerating system, so we start to see the most interesting features of these solutions, that they contain radiation. Okay, you see what we are doing here. We found the general solution. Of course, for a static problem, then it boils down to what we have already done in electrostatic and magnetostatics. Then if you allow some movement, but we know accelerations, then we have some class of solutions, the simplest of which is this linear Vickers potential. But what is really interesting is to see what happens when you have your source that is really changing in time. Okay, so that could be quite complicated, but essentially it's enough to study the case in which you have an oscillating charge or an oscillating charge distribution. And because it's oscillating, it has some acceleration. And what we see here is that there is going to be some components of these fields that are they are not damped very fast with the distance. They go down like 1/r, and that's what we call radiation. Okay, so if you have an oscillating or accelerating charge distribution, what you discover is that you have radiation. You have a field that is felt very far away, and it has certain characteristics. So let's study this case. What I mean by an oscillating source, I mean that I pick this charge density and current density to be of the form you have some distribution, and then the time variation of this distribution is like this. I put a time variation. When you see this, it's always the real part of this, right? Remember the harmonical oscillator. And similarly, for your, you have some distribution of charges, of currents, and the time variation is very simple. It's just a cosine of omega t. But it's easier to write it as an exponential and then consider the real part. And now I want to study under this assumption. Let's just study. It's enough to study the vector potential. Then from that we derive the because maybe just an aside here. If you have this kind of time variation that is just oscillating, that means that also E and B essentially will be oscillating function, right? But then you see that the Maxwell equations sort of simplify because, for instance, the curl of E, right, that is, then it has here a time derivative of B, but because the time derivatives only see the oscillating part, you see that this is going to be just minus I omega, the time derivative of B, with a C or not, depending on, let's not put it the C, then we are using the international system. And similarly, the other equation that I write with H, it has the other sign, so it's like this. Okay? So you see that, if you put back the units, you see you can always get the E field from the B field, right? Right? In particular, if you look at here, this is the correct equation, but now let's assume that we are in the vacuum. So you see that you get, so the H, it has the mu, so here you can replace E, right? If you put the epsilon naught, and here you can replace the B if you put the mu naught. So that means that E is equal, you take it on the other side, to I C K epsilon naught, the curl of H. Or, because C is always 1 over the square root of epsilon naught mu naught, this is I over K, the square root of epsilon naught mu naught, the curl of H. Okay, so, I mean, what I want, sometimes this is called the impedance of the system, because with the analogy of the vacuum, with the analogy of what you have in the circuit. But the point anyway is that if you know the magnetic field, then you can find the electric field for these fields that are oscillating in time. So that's why it's enough to study the vector potential. So let's study the vector potential. So I have this solution. Let me write it more explicitly. And to do that, I introduce. Ah, this? What? No, but this I'm just saying in the vacuum. I'm outside these charges. So I'm going to compute this potential at the distance r outside all sources, okay? And there, they are related by the Maxwell equations in the vacuum. In fact, you see here I use epsilon and mu naught. I'm in the vacuum, okay? Is this clear? I mean, this is, you have J if you are inside the charge and current distribution, but once you are outside, you are in the vacuum, so you can use the Maxwell equations for that. So to make this explicit, I should reintroduce the delta function. Remember that this retardation was essentially the integral over dt prime of a delta function. So let me write that back. That means I have j r prime t prime r minus r prime, and then I have this t prime plus r minus r prime divided by c minus t. That was the retardation. So, but now j, I'm assuming the j is in this form, right? So you can replace here the j I wrote there. So j r e to the minus I omega t. So you see that in this case, when you do the delta function, you replace again t with this retarded time, but in this form. So in this case, this integral is in the form d3r prime. You have your jr prime, and then you have this exponential that has been shifted. So I write it like this. I introduce k. So let's introduce k that is omega divided by c. So you have k r minus r prime minus I omega t. And then is sitting on this 1 over r factor. Okay? And then you know that H is just 1 over mu naught, the curl of this quantity. So this is A. Then when I have A, I can compute H through these usual things. So, okay. So clearly now, to proceed, I have to say something about this charge density. And essentially what you do is you have to assume something about the distance from this distribution of charges. Usually this is done by defining 3 regions, right? Because say here is where you have all these charges and currents, okay? And so this source is going to have some characteristic volume that you can characterize with some diameter. Let's call it d. This is the d, okay? And you are at a certain distance from this source, so this is the source. And you are here at the distance r, okay? And then the other, you see, you have D and R. So if you are very close to D, R is going to be not much bigger than D, and if you are far away, then D is much smaller than R. But in the problem, because you have an oscillating source, there is another scale that is relevant, that is the wavelengths of this oscillation, right? So you can introduce another scale, lambda. If you call lambda, so you have omega, that is the characteristic oscillation frequency, so you can call 2 pi c over omega. So this is the characteristic length of this oscillation, okay? So you have 3 parameters, and usually if you go and read your book, you will see that you have a near, also called static, you see why in a second, zone. Okay, so this is essentially the zone where R is always, we are always very far away from D, okay? But, so D is much smaller than R, so you are sufficiently far away from D to not have to worry too much about to be inside that charge distribution. But also, you are, R is much smaller than the characteristic lengths, wavelengths of this oscillation. Okay, so that, I don't know. This is lambda. So this is a regime in which you see lambda is very, very big. Okay, and then you understand why it is essentially the static zone, because essentially this thing does not oscillate. I mean, it's like if you have a wave coming, but the wavelength is much bigger than, so you are closer to the source than the first wave, okay? So for you, essentially, a static is not oscillating, because you don't see this oscillation. You have to, okay, it's clear. Then you may have an intermediate zone, induction is called, where you understand this is still true, but now lambda, the wavelengths, and the R they are comparable. So essentially, you see that is a wave, and is comparable to your distance. So it's like this one. So before it was like. Okay, and finally, obviously, you have a far zone that is called the radiation zone, that actually is the most interesting, at least for me, where D is, so now you have that D is much smaller than the wavelengths, and the wavelengths is much smaller than R, okay? So now it's like this. So let's discuss briefly these two. I mean, we skip the intermediate zone because it's more complicated. But the other two are, they can be discussed in some detail. So let's start with the near zone. So now I discuss this vector potential in the assumption that I'm in a near zone. This obviously implies some simplification on the function that I have to integrate it, and so I can get some sort of because you see, if we are in a near zone, that means that this KR term is very small, right? It can be neglected because R is much smaller than the wavelengths, right? So that means, you see, the wavelengths is here, that K, that is omega over C, K is omega. That means that KR is much smaller than 1. That means I can, essentially, this is 1, right? Because the exponential of 0 is 1. Okay, so essentially I can write that the integral in the approximation in which this is close to 1. In fact, it goes to 1. But then that integral simplifies very much. It simplifies very much because the potential now R of t is mu naught divided by 4 pi. Then you see this I neglect. So, okay, I have this oscillating part that I can put even outside the integral, right? Because there is no. Yes. La radiation, c'est où? This. Radiation, yeah. Ah, you just want a yeah. Radiation. Okay, we are good. So you see, then I have this term here that is sort of trivial. It's just following in the oscillation the source. Then this is not there, but then I have left exactly the same integral that we had a few weeks ago when we were doing magnetostatics. And in fact, I can do the same expansion, right? So I have e to the minus omega t that is still there. But so maybe let me. I have this term here, but then I can expand this in the usual way, right? Because it's 1 over r minus r vector prime. So I have I can expand it in spherical harmonics. You remember that, or? So I go back to what we did a few weeks ago, and I have my expansion in spherical harmonics. So I have a path that depends on the position of r. So that goes outside the integral. And then I have the path, so I have e to the. And then I have the other spherical harmonics, that is the one that depends on the theta prime and phi prime, so the coordinates inside the volume over which I'm integrating. And there I have also this charge distribution, then r al prime, y l m dot of theta prime, phi prime, and here I have my d3r prime. So for this reason, you see this near zone is called the quasi-static, because if you forget about this, this is exactly what we would have written 2 weeks ago doing the magnetostatic problem. So the near zone, essentially, you see what you would have seen if the source had not really oscillated, because you have exactly the same solution, and the only difference is that it's modulated in time by this cosine, simply because it's moving. But it's moving slowly with respect to you. So it's not really that interesting. And in fact, we can move on to the next, that is the far zone. The far zone. So the far zone means that is this one, and now you can expand this. So essentially, you can expand this distance, right? This is a far zone. So the first effect is that this is essentially r minus n dot r prime, where n is a unit vector in the direction of r. So it's r divided by r. So under this approximation, my potential now for the far zone is this mu naught over 4 pi. Then you see that here I can use this approximation, right? So I have e to the I k r that I can pull out from the integral, e to the I k r. Then I have minus I omega t that I can always pull out from the integral because it does not depend. Okay. So that looks like a wave. And then downstairs I can pull out this r. So r goes outside. And I'm left with the integral over the charge current distribution in r prime, right? And I have a leftover here in this exponential because you see I have r, but I also have this unit vector dot r prime that comes like minus I k n dot r prime, d3 r prime. So I don't know if you, this looks like an outgoing spherical wave, right? Do you recognize that as a spherical wave? You see, it goes like 1 over r, and then it has an exponential ikr. So that's it's a spherical wave. And then there is this factor that depends on the precise distribution of these currents. Okay. In fact, you can further simplify this because I can use the Taylor expansion for this exponential, right? I know that the e to the x is equal to the sum from n equal to 0 to infinity of what? Yes. So maybe let's write it a little better. I pull out, so I replace the exponential by the sum in the Taylor expansion. You see the Taylor expansion, now I erase it, but I have minus I k to the n factorial, and then I have the parts that depend on r prime, so I have my current is still there, and here I have all these powers of r prime that were in the exponential, so to the n. Do you agree? And why I'm doing that? Because you see here, they look nice, because I can then look at the few terms in this expansion, and I will get back something that looks like a dipole, a quadrupole. So I'm back to my, I hope, our old expansion in terms of multipoles. Okay, so I'm going to have a radiation field depending on some multiple expansion here, and I can study, for instance, the lowest order, that is the dipole. That is what we are going to do in a second, if you are happy up to this point. If you are, I guess, well, I need some blackboard, so let me erase this. So for instance, what if I take just the first term in this expansion? Right? If I take the first term, I don't have this factor. I mean, essentially, I just take the 1 in this expansion. So I have A of R and T that is equal to what? Mu naught 4 pi. I have this spherical wave. But then I don't have anything else. I just have this integral over J r prime d3 r prime. Right? So this is the leading term in a way, is the first term in this expansion. And really we will stick essentially to this one. But you understand you can go on and you will produce other terms. And now, as usual, we need to do some, we have to massage this term in such a way to write something that we recognize. And you see that if I do, I can do this integral by parts. That's a usual trick, right? Because there is this big garbage bin that we call the infinity, right? So if we do something by parts, whatever is an infinity we throw away because we assume that everything decays fast enough not to worry much about the infinity, even though here we are sort of borderline, because with all this radiation going in and out, it's not obvious that we can neglect, but certainly here we can neglect in this integral because we are talking about a source that is localized, okay? So let's do it by parts. So by part, I throw away whatever, I don't have any charges or currents at infinity, so I can throw that away, and I'm left with the minus r prime. Then I have to take the derivative of this, but the derivative of this is really a gradient, right, in this language. It's a gradient on this r prime, so I guess it's not a gradient, it's a divergence over the volume r prime, okay? So I've done this by parts. And this is nice because looks like an electric dipole moment, right? Because this is equal to you see, you can pull back this in, so this is minus omega, the integral of r prime, right? This is what? You know, you have this, yeah, the charge conservation. Okay? Yes or no? Yes or no? It's a simple question, no? You by parts, and then you use the charge conservation. This oscillates in time, so the time derivative is this again, so you get this omega. So the whole thing, so this was the integral, so that means the whole potential can be written in a very, so I collect this there, so I get minus I mu naught omega divided by 4 pi. Then this, we already have a nice name for this, is the dipole, is the electric dipole moment, right? So essentially it's P, and then I have this spherical wave, Kr minus I omega t divided by R. You see, every time you get an omega here, you can always think that, because this P itself, right, is, right, you see, it's like a time derivative of P. So in a way, this is like proportionate to the time derivative, one time derivative of P. That's a useful way. Well, in a second, we will see why. So now, so okay, so that's the solution for, well, it's not the full solution, obviously. We have taken the lowest order of this expansion, and we are in the far zone. So it's it's a special case of a special case. You mean the omega? Did I? It's no. It's this is equal to minus. Huh? Okay. It depends if you take it. But I mean, it's not very important. I mean, this sign. So let's not sweat about it. So now I can compute the radiation. I can compute H and E, the field strengths, the fields in the radiation. So in the far radiation zone, having the potential, now I can compute this. And you see it's very simple because I just have to so H is 1 over mu 0, the curl of A, where A is given by that. So if you, so you have to take the curl. So let me write the result. So K is omega divided by C. So this is omega squared divided by C. Then N is this versor, is a unit vector point at the observation point cross P E K R minus omega T divided by R. Let's actually this can be well, just a second. And then E, because of what I wrote there before, is just H cross N with this factor mu naught epsilon naught, right? This impedance. So you see you have a omega square here. So that means this is proportional to the second derivative of this P essentially. So this is the field is proportional to the acceleration of your oscillating charge, as it should be. As before, we saw if there is no acceleration, it's moving with constant velocity, you don't have this radiation field. So that's important. If you have an accelerating charge, then you have a radiation field. Otherwise, you do not. And the E field is just this combination, so it goes the same way. Now, I don't have the energy to do the same for the near zone, but you understand that is not very much different. Again, here you can take the leading term in this expansion, okay, and do the same computation, but you are going to discuss. You see, this was exactly, we said, this is the same solution that we had in the static limit, except for this overall oscillation. So it's not surprised that you are going to have a magnetic field and electric field that are exactly the same as the static solutions, right, for the dipole, except for this overall phase. That is the cosine of omega t. So in the near zone, you can write the solution, or you can rederive if you want. So in the near zone, it's just like it was before. So the H field is going to be I omega for pi n cross P. But you see, 1 over r square E I omega t. And E, you can get it from a similar formula, is going to be the electric field for a dipole that you remember. But you see, the two important thing is that first it goes like 1 over r squared, so it's a field that goes down much faster than the radiation field that is characterized by the 1 over r behavior. And second, it has only 1 omega, so it goes like essentially a first derivative. So it's something that you have even if you don't have an acceleration. So essentially it's like a slowly moving dipole, say with constant speed, is going to have this, but not this one. Okay? How much power is given off by this radiation? That's the next question, I guess. Well, that's easy to estimate because all you need is your Poynting vector. So for a given solid angle d omega, if you have to do some time averaging of your power, and it's given, so you have to take the real part because you have this oscillating thing, and this is given by r squared, the component n that is always the one pointing toward the observer, and then the Poynting vector, so E cross H. Well, because H here is complex, you should take H conjugate and then take the real part. So that gives you the power when you average. Right, this comes from the integral, and then so if you plug in, you see, then oh damn, oh no, it's here. No, sorry, the radiation one. You can plug them in, right? You have H and E. They are given by this. So I've done this computation. I get k to the 4th, 32 pi square. Then you get this mu square root of mu naught epsilon naught from the E, and then inside you see you have this n cross p cross n square. Now, if you introduce, now you can introduce you have a solid angle, so you define the sine of theta to be one of your coordinates. So then you can do this vector product, right? And you see you have the c square k to the 4th, 32 pi square, this square root. And now this thing is just the length of your dipole square, right? Then you have this. So if n, the angle between n and p is theta, this is just the sine square of theta, like this, right? And now you can do the integral over so the total is just this integral. So 32, you get this factor from the angular integral, you kill 1 pi, and then just mu naught epsilon naught. So the total power emitted by an oscillating charge at the leading order in the expansion, so when you only retain the dipole term, is the square of the dipole, right? And you see it goes like the 4th power of the frequency. That's a famous term that we will discuss in a second, or maybe a little longer. Well, okay. So if you have something oscillating, it emits radiation. So that's energy that is flowing away. Okay. And so it loses energy, or it emitting energy proportional to the fourth power of the frequency, right? That is like the fourth power of 1 over the wavelengths. So that means that if you have light, for instance, exciting atoms in the atmosphere, right? So these atoms start emitting with this. The atoms are a little bit like sources described by an harmonical oscillator oscillating, and they emit proportionally to the fourth power of their frequency. So that means they emit much more, right? At higher, they emit more at the higher frequencies than lower frequencies. That, for instance, is the reason why the sky is blue, right? Because blue, right, is higher frequencies than red. You have this stuff oscillating, and it emits much more in the blue than in the red. So when you look at the sky, the atoms there, they are emitting more in the blue than in the red because of this formula. So that formula is called this fact that it goes like the 4 power of omega, or 1 over lambda to the 4th, is the law of the blue sky. Of course, this is also the reason why the sun is red just before a sunset, because the light coming from the sun goes to excite these atoms. So the blue light is diffused much more than the red one. So the light that was originally white from the sun, the blue component gets depleted, and you are left with the red part. Okay, so that, I guess, it doesn't have a name, but it explains why the sun is red at the sunset, and this explains why the sky is blue. So you see, very important application of this computation. If you ever wonder why the sky, most people just, oh, it's blue. But it could be green. Why it's not green? Well, okay. So now this is. The mass. There is no mass here. They are just massless fields.
Yes, because I'm currently in my mind that of electrons, while in the first theory, while they're moving, they should radiate and so on and so forth.
Yeah, no, but that's okay. No, this is just pure electromagnetic field, so there are no masses. Then maybe I confuse you a little bit because I start talking about these atoms in the atmosphere. But there is a different system, really, because there you have to think of the atoms as harmonical oscillators, right? And then they go back and forth like this. Okay, so there you have the mass. But the mass has to do with the motion of this atom, but not with the radiation. So here we are just assuming that this is moving with this, you remember the current, well, I don't have it any longer, but the current was just the static part and then oscillating like this. So I guess this is just like this. Actually, this is just a charge. And if this charge is moving like this is the electromagnetic field that is coming out. So there is no mass here. You need the mass if you want to know how this moves, right? But that's a different problem. There you have to use the Lorentz force. Then you write the Lorentz force of the motion of this because of the presence of some electric and magnetic field. Actually, that's a complicated problem because you understand, we are not going to discuss that, but since we are talking, because once you have the particle moving, and then we have solved the problem of how this particle moves because of external electric and magnetic fields, right? The first class. Now, you see this particle is moving, and if it is accelerating, then it is irradiating, right? You have radiation. and you see it's losing energy. So that means that the Lorentz force is not correct any longer, because you have a sort of a reaction of the particles, because the energy of the particle is changing because it's radiating electromagnetic energy. So in principle here you should study the back reaction of this on the particle, and you understand that becomes a complicated equation that, however, has been discussed. If you look at the Jackson, there is a chapter where this is discussed. You see, this goes back to the problem of the electrons. So say you have the atoms, and then you want to make this a classical system. So you have a proton and an electron. Now they are attracted, so the electron is bound to be in some orbit, like a planet around the sun, and this maybe was the idea that people had. But the electron is going around, very nice. But because of this guy is going around, right? So you know that, I hope after all I taught you in classical mechanics, that an atom going around, an electron going around is accelerating, right? And so it's accelerating, so it's emitting radiation, so it's losing energy. So the idea is that this guy is going around, losing energy, and so eventually falling on the proton. So this was the original argument against the classical atoms, because they say they cannot last, because electrons radiate and then they eventually fall. This is not completely correct, however. It's one of those things, you know, that people repeat and eventually they write in the books. But actually, if you have more electrons, you see, it cannot be completely right, because you know that if you have a wire, that is not radiating. If you take a wire, right, like this, there is no radiation. Right? The electrons are going around. So how come? The fact is that if you have more than one electron, you can have interference among the various electrons, and the radiation actually can be almost completely destroyed. That's the reason why, if you have a symmetric things, like if you have a charged sphere and then it's rotating, it's not radiating. So a single electron is radiating. But if you have many electrons distributed in a uniform way, you understand there cannot be any radiation simply because of the symmetry of the system. So if you take a uniformly charged sphere and you rotate it, that is not radiating. So the idea really should be that the atom, the classical atom, should be some form of uniformly distributed set of electrons, and that you can always arrange in such a way that you reduce the radiation. I think I even have an exercise or something like this, something similar. But that's sort of, I mean, it's just to say that the usual argument that you find in the books is not completely correct. I mean, that because of this, the classical atoms, I mean, they were not stupid at the time. They knew about this, so they knew how to make this stable. But of course, the reason why the classical atom is not correct is the experiments. I mean, they do not radiate following this law, because you know that they radiate in a quantized way, right? They do not radiate like this. This is a continuum spectrum of radiation. Why, if you have an atom, it's not radiating like this. So that's the reason why you need to quantize, not because it falls on the. This is kind of naive. But okay, if you have a single electron, then this is true. Okay, I don't know if I answer you or I completely confuse everybody at this point. So now that we are happily confused, we can move to so this is the dipole radiation, right? So I guess I want to or maybe I give you this as an exercise. Yeah, I've been a little slow, but okay, well, let's start. So I guess what I wanted to do, well, originally I thought maybe as an exercise, but also this is the general derivation of this dipole thing. But you may wonder, okay, I didn't understand a thing. Maybe that's your feeling now. I mean, he has been just expanding and doing. So you just blacked out. And because you are clever, you may say, well, okay, I don't care about this derivation. He said that is a dipole, so I can take a dipole that, let me take this plus here and minus here, okay, something. So this is a dipole, right? And I can write this, the potential for this dipole, right? And I think this is what is done in the other book. So so I don't know. Should we? Is this a homework or should we? So you see, then I go R here. I sit here and I look this at this problem that I have my dipole, and I study the field of this dipole, and I should recover the same result that I had before. Okay, so it's a sort of a double check. This was the way that this was the way that this was derived by Hertz. So I guess this system of a simple dipole radiation is called the Hertz oscillator or something. So the idea is what? I take again my potentials that I already derive and so these linear Vickers potentials. No, I'm a little uncertain whether to dig into this or do you want to try and do it as a homework or I see that you are not enthusiastic. So so we know that the potential here is like this. Is the one we started with and has to be computed at the retarded time. Okay? And similarly for A, you take again this linear Vickers potentials. It's just the same things, but with the velocity of the retarded. Okay. So if you have this system, the P, right, is just let's call this this distance r prime, so half of this distance is r prime half, and then you have the other half on the other. Then r prime E is the dipole moment. And r prime is all there is in the volume, the previous computation in which, because I start, instead of expanding the general charge distribution, I just start with the leading term, that is this dipole. Then I have, and so I can plug that in, because you see that I have E, the velocity of this is minus E r dot prime plus E r dot prime divided by 2. So I guess is with a minus here. So it's minus E r equal minus E r dot, that is P dot. P dot. Okay? So you can replace in here, in there, this expression. And you see, you have, this is for a single charge, right? And you have to do it for two charges at the two different points. So this should be for so this is the general potential, and I have a potential for one charge in plus r prime divided by 2, and the other opposite and symmetrically there. So I have to write this potential. So write this potential. So it's useful to introduce, as is done in the book, r minus plus this r prime divided by 2. Because you see here, you have to put one charge in plus r prime divided by 2, the other charge in minus. So you may as well put one minus, this is the one in r minus r prime divided by 2. So r minus dot, so V is r prime dot divided by 2, so it's like this, retard. And then you have the other charge, the one opposite, so it r plus, minus r plus, r plus. So here is in minus r prime, because it's the one in minus r prime, divided by 2c dot. Okay, I don't write the same you should write for the vector potential, you understand. Then again, so for the vector, maybe, and for the vector potential, so this was the scalar potential. The vector potential is just what? You divide by C, and you replace V with R dot prime divided by 2 here, and here divide by C, and then minus R dot prime divided by 2. Okay, so then this is the A. So let's use A as before. But you can do the same with the scalar potential. So now you have to do two assumptions. First, that the R plus minus, you see you are far away as before. You are in this radiation zone. So you are sufficiently away from this system that essentially you can approximate this by R, right? And the other thing is that I'm assuming that this thing moves, is oscillating, but not too fast. So you can sort of neglect relativistic effects. And therefore, you see, you can expand this, and you get that is about, so you see essentially you can check, let me write this result, is r dot prime, this is the velocity of your divide by r. Or, you see, you can use the definition of P is P dot CR at the retarded time. This is the same result that we had before, essentially. Well, actually, precisely, as it should. Now, if I take the curl of this, right, you get the field and the same that we had before. If you take the yes, you can also well, this was the homework in a way to rederive the result that we had from the top down, from the bottom up. So again, you see it goes like the velocity here. When you take the field, is going to go like the two dots, So if you want, I rewrite. So if you take the curl of this, you get the P dot dot cross R, C R square, I think C square. And E is just the same thing, but you have to take the, so I put the cube here, but then you have cross R. That I think is what I had before, I hope. And again, then you can, so you see it's the same things rederive from just taking that term, not by reducing the general expression. And if you do the Poynting vector of this, then again you can compute the radiation and the total energy and the law of the blue sky. So okay, so that was the homework, but I guess I did it for you. Notice that you remember that the power emitted was like the sine square of theta, right? I mean, if you have something like this, you are here, and this was theta. So that maybe is worthwhile to notice that. So you don't have radiation emitted in the direction of the motion, right? Because you see that the radiation goes like the sine of the angle. So it's peaking, I mean, it's zero, and then it's peaking orthogonally. That's a particular, is a property of these, of this kind of radiation. This is called synchrotron radiation when you have a single electron, and so it's zero in the direction of the motion, and then it's open up and reaches a maximum according to this sine square, right? If you had included a more complicated system like the quadrupole, you remember that we studied the quadrupole term of this, then here you would have some corrections. That I guess, so this I can always write it like this, right? So let me 1 over C, sorry, with the R. And so RC square. So this is, now I'm looking just at the radiation field. So the leading term is this P cross N. And just for reference, I put here that if you introduce, you remember this Q, that is the quadrupole, no? This Qij equal the integral 3xi xj minus r squared delta ij, the rho d3r. So if you introduce that, okay, it goes like this. Then you have higher term, where this is the component of this tensor projected on two of these unit vectors, and it goes like the triple derivative. So I guess the first time that we see a triple derivative, because the acceleration is 2 dots, but this is 3 dots. And so you can. So let me give you homework, and then I stop. So the homework I thought is kind of interesting is the radiation of rotating. So it has to do with the atom in a way, rotating charge. So you take a charge moving on a circle of radius a. So that means the position of this charge is equal to the radius times, if you introduce some Cartesian coordinates, so the unit vector in the direction x, let's say it moves with the frequency omega naught. So it's moving like this, right? So it's in the class that we discussed previously. And therefore, it has a dipole moment that now I call D, because that's how it's written in the book, like this. So now, by using this stuff, you can compute H, E, and S, and also the total radiant power, as I did before. So you have to convince yourself that, in this case, explicitly you reproduce this formula that I show you, this of the blue sky, right? That goes like the 4th power. So I just plug in this solution the case of the. Actually, in the same. If you go to this Grainer's book where this example is discussed, you will see that then he does the one with 2 charges moving in this way. And you see this is a system that has a quadrupole. So read the solution or do the computation if you want, and you will see that this system already radiates much less than the single charge. So it's not true that you may expect that because you have 2 charges you have even more radiation, but no. If they move in a particular way, like completely out of phase, then they interfere with each other, and you will see. Check that the power emitted in this second case is much smaller. In fact, it goes like is the 6th power here divided by c to the 5th. So this is it's a small term. So it's much smaller than this. So you already reduce by very much the amount of radiation given off by this system just by adding a single charge. So you see, you can think of the atom as adding charges moving in a symmetric way, in such a way to reduce this emitted power by many order of magnitudes.